One day will come when the universe, at least as we currently understand it, will come to the end of its journey. About 3 decades ago, the scientific community had largely reached a consensus about that ending. In a distant future stretching trillions of years ahead, galaxies would continue drifting farther and farther apart without end. Stars would one by one run out of fuel, cool down, and fade away. Even the most extreme entities, black holes, would gradually evaporate until nothing remained but a cold, dark, and eternally silent space. This scenario is known as the Big Freeze, the inevitable consequence of the universe's accelerating expansion, a process driven by the mysterious phenomenon known as dark energy. But that may no longer be certain. New observational results from the Dark Energy Spectroscopic Instrument, DESI, are revealing a startling possibility. The influence of dark energy on the universe may not be constant, but could be weakening over time. If this is true, then what happens when the invisible engine driving the universe's expansion gradually loses its power? Could the ultimate fate of the cosmos be standing on the brink of an entirely new turning point? You're watching Cosmic Light, and in this video, we'll explore a profound shift in how humanity understands the universe, and why dark energy, once thought to be unchanging, may actually be gradually fading. Are all modern cosmological models fundamentally flawed? Or is there another explanation still waiting to be revealed? To find the answer, we need to turn back the clock to the year 1998. At that time, scientists already knew for certain that the universe was expanding. Based on the revolutionary observations made by Edwin Hubble nearly 70 years earlier. But the big question remained unanswered: how fast was the universe expanding? And would that expansion slow down over time? Intuitively, this seemed reasonable. Gravity, after all, always tends to pull things back together. The answer lay in a key number, the Hubble constant, the quantity that describes the rate at which the universe is expanding at the present time. Remarkably, this number can be determined using 2 completely different methods. Strangely enough, these 2 methods do not yield the same result. This disagreement has become one of the greatest mysteries in modern cosmology, often referred to as the Hubble constant crisis. In today's journey, we will focus on the second method, redshift, and its role in shaping our understanding of dark energy and the ultimate fate of the universe. Throughout the history of modern astronomy, scientists have used the redshift of variable stars as a kind of cosmic yardstick to measure distances across the universe. But over time, they realized that there was another tool that proved to be even more reliable: Type 1a supernovae. We know exactly how bright Type Ia supernovae are because they all end in the same way. They are colossal thermonuclear explosions that occur when a white dwarf in a binary star system siphons off too much material from its companion, and, 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 It is this uniformity that makes them perfect standard candles. By comparing a supernova's true brightness with how dim it appears from Earth, astronomers can precisely determine its distance. Sounds simple enough, right? But it was precisely here that something unusual emerged. When two independent research teams observed more than 50 Type Ia supernovae, they realized that these explosions were dimmer than expected. Further analysis revealed a truly astonishing reason. Those supernovae were much farther away than existing models had predicted. And this led to a shocking conclusion. The universe was not slowing down under the pull of gravity as once believed. Instead, its expansion was accelerating. It seemed as though something invisible was quietly pushing all the galaxies farther and farther apart. To visualize this, imagine drawing dots of ink on the surface of an uninflated balloon. As you blow air into it, the dots themselves do not move across the surface, yet the distance between them increases. Not because they are fleeing from one another, but because the very space in which they exist is expanding. This discovery did not provide clear answers. Instead, it opened up a cascade of new questions. What force was driving this acceleration? The truth is, to this day, we still do not know. That mysterious force was given a name: dark energy. Most scientists believe it is a fundamental property of the vacuum, the intrinsic energy of empty space itself. Other hypotheses suggest it could be a form of energy field or an exotic fluid permeating the universe. Some have even proposed that it might arise from deep defects in the fabric of space-time itself, such as thin yet infinitely extended cosmic strings. And there are also those who believe that dark energy may not exist at all. That the problem lies in our incomplete understanding of general relativity when it is applied on cosmic scales. But whatever it truly is, dark energy remains tightly linked to the accelerated expansion of the universe. And it has forced science to rewrite the entire story of the cosmos. This discovery was so profound that the scientists who led the 1998 research were later awarded the Nobel Prize in Physics. From this point on, a new cosmological model emerged, the Lambda CDM model, also known as the standard model of modern cosmology. In it, lambda represents the cosmological constant, a concept originally introduced by Einstein, and now used to mathematically describe dark energy. CDM stands for cold dark matter, a form of matter that neither emits, absorbs, nor reflects light, yet reveals its presence through its gravitational effects. The name can be misleading. Dark matter and dark energy are not directly related to each other. They share only one thing in common: we do not understand them. While dark energy governs the universe's accelerated expansion, dark matter acts as the gravitational scaffolding that allows galaxies to form and persist. And everything we can see, from stars and planets to the human body itself, is merely ordinary matter. also known as baryonic matter, an almost unimaginably small component of the overall cosmic picture. Based on a wide range of independent measurements, the scientific community has reached a consensus. About 68% of the universe is dark energy, 27% is dark matter, and only around 5% is visible matter. About 68% of our universe is made up of something we do not understand and cannot even measure directly. Yet, within the current standard cosmological model, there is a crucial assumption: dark energy, denoted by lambda, is considered to be constant. Nearly all calculations about the universe are based on this premise. That very assumption tells us that the universe is expanding at an ever-increasing rate, and therefore its ultimate fate is almost predetermined. A future that is cold, lonely, and irreversible. Under that scenario, galaxies will continue drifting apart as the very space between them keeps stretching. Stars will eventually exhaust their fuel, fade away, and grow cold. Heat and energy, once the foundation of all structure, will be stretched and diluted to unimaginable extremes. In the end, the universe will approach a state just barely above absolute zero, concluding in what astronomers call the Big Freeze. But what if we were wrong? For the first time since dark energy was discovered, there are signs that we may have touched upon one of its deeper properties, and it is not what scientists expected. In 2024, the Dark Energy Survey released the largest supernova dataset ever compiled from a single survey, based on the study of the deaths of more than 1,500 stars. At first, everything seemed fine. The data were consistent with the hypothesis that dark energy is a constant. But when scientists combined this dataset with other independent sources, including the cosmic microwave background and previous galaxy surveys, a subtle discrepancy began to emerge. Something did not quite add up. The numbers suggested that dark energy might not be fixed, but could be changing over time. If this is true, then the entire way we describe the universe must change as well. Our current mathematical tools may no longer be sufficient. Old conceptual frameworks would need to be replaced by entirely new approaches. And to sharpen our thinking for questions like these, humanity has always needed the right tools. That is why Brilliant exists, as a companion for the mind. Not just for mathematics or programming, but for developing deep thinking, asking the right questions, and connecting complex ideas. The very core skills of cosmological science. However, returning to dark energy, despite the promising initial results, they are still not sufficient to serve as definitive proof. Significant uncertainties remain. And to determine whether this is a genuine signal or merely a statistical illusion, astronomers need a much larger and far more detailed picture of the universe. That is when the Dark Energy Spectroscopic Instrument entered the game. Installed on a 4-meter telescope in Arizona, DESI was designed with a single purpose: to test whether dark energy truly is a constant. With the ability to collect light from 5,000 galaxies at the same time, DESI is mapping the positions and recession velocities of around 40 million galaxies and quasars. Spanning more than 11 billion years of cosmic history, no previous project has measured the universe's expansion history with such precision. This is not the effort of a single nation. It is a truly global endeavor, bringing together more than 900 scientists from over 70 institutions around the world. And then, in 2025, the first core datasets were finally released. They include results from the first 3 years of the survey, with 2 more years of data still waiting to be revealed. What emerged from those numbers was truly extraordinary. The Dark Energy Spectroscopic Instrument used data from nearly 15 million galaxies to construct the largest 3-dimensional map of the universe ever created. This map allows us to fly through millions of galaxies, each containing between 200 and 300 billion stars. Earth sits at the center of this animated view, and every point of light you see is not a star, but an entire galaxy in its own right. Blue colors represent galaxies that are very far from us, while the bright white points indicate structures that are closer. In other words, this image is packed with galaxies to a degree that far exceeds human intuition. From this vast trove of data, astronomers measured baryon acoustic oscillations, or BAO, using more than 14 million galaxies and quasars. BAO can be understood as fossil echoes of sound waves that rippled through the early universe, when the cosmos was still a hot, dense ocean of plasma. In a visual sense, the brighter regions represent sound waves propagating through that primordial sea of matter. As the universe cooled, these oscillations were frozen in place, leaving behind regions where matter became slightly denser. Over hundreds of millions of years, these denser regions continued to attract more matter, eventually collapsing into stars and galaxies, and forming the cosmic web we observe today. By tracking how the scale of BAO structures changes over time, researchers can calculate the universe's expansion rate at each stage of cosmic history with extraordinary precision. But they did not stop there. DESI data were combined with several other independent measurements, including the cosmic microwave background, the redshift of supernovae, and weak gravitational lensing, the way light from distant galaxies is subtly bent by gravity along its path. And when all of those pieces were placed side by side, a troubling picture began to emerge. Not only are there signs that dark energy is changing, but the analyses also suggest that its influence is weakening over time. In fact, the repulsive effect of dark energy may have decreased by about 10% over the past 4.5 billion years. You can picture it like a car that is still accelerating, but the foot on the gas pedal has begun to ease off. The car keeps speeding up, but not with the same intensity as before.
Similarly, our universe is still expanding at an accelerating rate, but that acceleration is no longer as strong as it was a few billion years ago.
And if dark energy is not an immutable constant, but a quantity that evolves over time, then it means our standard cosmological model is missing something, and that something is enormous.
If this groundbreaking discovery is confirmed, it could lead to an entirely different fate for the universe.
Instead of a big freeze, in which the universe expands forever and ends in coldness, darkness, and isolation, we may be heading toward a far more dramatic scenario.
If the influence of dark energy continues to weaken, or even becomes negative, the expansion of the universe could slow down, come to a halt, and eventually reverse. Recall the primordial power of the Big Bang, the moment when the universe erupted with enough energy to give birth to every galaxy and every star.
Now imagine the opposite, a big crunch in which everything turns around, rushing back inward, collapsing into a single point with an intensity great enough to erase every trace of existence.
I've talked before about the Big Crunch scenario, as well as other theories in which physics becomes truly strange in the final stages of the universe. If you'd like to explore this further, I recommend watching the video linked here.
And now, if dark energy truly is an evolving variable, then perhaps there is another variable, even more important. One that will determine not only the fate of the universe, but our place within it.
The implications of these results are profound. At the very least, they show that our current cosmological model is incomplete.
At a deeper level, this could imply that general relativity needs to be extended or modified on cosmic scales, and that particle physics may still be hiding new fields, forces, or interactions that we have yet to uncover.
But before rewriting any textbooks, science demands one non-negotiable thing: certainty. And at this moment, we are very close, but we have not yet reached the finish line.
In science, the level of confidence is measured by a concept known as sigma, or standard deviation. The higher the sigma, the lower the chance that a result is merely a statistical fluke.
In the search for signs that dark energy is evolving, this sigma value has been steadily rising. Data from the Dark Energy Spectroscopic Instrument alone have pushed us past the 2 sigma threshold, corresponding to roughly 95% confidence.
It's an intriguing signal, enough to draw attention, but not enough to stake an entire scientific career on it.
when DESI is combined with other independent measurements, the confidence level surpasses 3 sigma, and in some data combinations even reaches 4.2 sigma, equivalent to 99.997%. This is considered very strong evidence, unlikely to be a mere coincidence. But in physics, very strong is still not enough. History has taught us some costly lessons. There have been results with similar or even higher levels of confidence that were ultimately overturned. That is why physicists usually declare a discovery only when it reaches the gold standard, 5 sigma. A famous example occurred in 2011 at the Gran Sasso National Laboratory in Italy. The result reached 6 sigma, even surpassing the gold standard. The probability of it being mere chance was vanishingly small. And yet, the truth eventually came to light. No particle had broken the laws of physics. The cause was simply a faulty fiber optic cable and an error in clock synchronization. The lesson is clear. High confidence does not necessarily mean absolute truth. Therefore, the road ahead for the hypothesis of an evolving dark energy is still a long one. DESI is now entering the 4th year of its 5-year survey, moving closer to its goal of measuring 50 million galaxies and quasars, and continuing to deliver ever more precise data. But DESI is not alone. In the coming years, several new missions will join what is set to become the largest investigation in the history of cosmology. Europe's Euclid Space Telescope and NASA's Nancy Grace Roman Space Telescope will extend these measurements to far larger volumes of space and to much higher redshifts, allowing us to peer deeper into the universe's past.
All of these projects share a single common goal: to determine whether dark energy is truly an immutable constant or merely a phase in the evolutionary history of the universe.
And if the second answer is correct, then what we are facing is not a minor tweak to the model, but a complete redefinition of the universe's fate. And then, in the coming years, the Vera C. Rubin Observatory will begin scanning the night sky with unprecedented detail. Its mission is to detect millions of supernovae,
creating a data set vast enough to potentially push us to the 5 sigma threshold, the gold standard of certainty in physics. Personally, I'm genuinely eager to see what they will discover.
But even as we wait, the new findings from DESI are already enough to make us pause and reflect. They bring humanity to the very edge of an entirely new perspective. Not only on the standard model that describes the evolution of the universe,
but also on the ultimate fate of the universe itself.
Now the question is no longer whether the universe will change, but in which direction that change will unfold.
Will the universe drift forever toward a big freeze? Cold, dark, and lonely? Or are we approaching a big collapse, where everything turns back on itself, ending in a violent implosion, perhaps laying the groundwork for a new cycle of rebirth?
I'd really love to hear your thoughts. How do you think the universe will end? Or do you believe it won't truly end at all, but simply transform into another state? Share your thoughts in the comments section.
Thank you for joining Cosmic Light on today's journey of cosmic exploration. If this video made you think, please give it a like and subscribe to the channel so you don't miss future discoveries about the universe and science.
See you in the next video. Wishing you fascinating reflections on the universe.